Welcome back to The Deep Dive, where we take a stack of dense research and distill the most important, surprising knowledge nuggets just for you.
Hey there.
So, today, we're going to be challenging one of the most fundamental ideas in reinforcement learning. We're talking about the very definition of success itself.
That's right. For an AI agent to learn anything, we have to define its goal with a reward function. And, this reward is the core language, but reward engineering is. It's notoriously difficult.
It really is.
It often feels like the single hardest part of solving an RL problem, because even if two different reward functions mathematically point to the same optimal policy, they can lead to just drastically different learning performance.
It's like a tightrope walk, isn't it? You might tweak the reward just a tiny bit, thinking you're giving the agent a helpful nudge.
Right.
And suddenly the agent either solves the task perfectly or, more often, it just gets completely stuck chasing some local maximum that isn't the real goal at all.
And if you look at the big RL successes from the past, like teaching systems to play DOTA or those complex robotic soccer games, they often required human experts to spend months, sometimes years, meticulously crafting that perfect reward signal. I mean, it's a massive bottleneck.
And that pain is felt most acutely in sparse reward tasks.
Oh, definitely.
Just, picture a giant maze where the agent takes 1,000 steps and gets a reward of 0, 0, 0, until it finally, maybe by pure chance, stumbles into the target state. Standard RL just completely falls apart there.
It has no signal to follow, no gradient. So the common solution is always to add some kind of dense surrogate reward, maybe based on, the distance to the goal.
But that's its own can of worms.
Yeah.
You have to tailor that function so perfectly that it always increases as you get closer, but without subtly messing up the actual optimal policy. It's so tricky to get right.
It is. It takes deep domain knowledge and, frankly, a lot of guesswork about discounted returns.
Okay, let's unpack this. What if we could just bypass that whole mess?
Well, that's exactly the proposal in the paper we're diving into today. To the max, reinventing reward in reinforcement learning.
They're proposing a paradigm they call max reward RL. So the agent isn't optimizing a discounted sum of future rewards anymore.
Instead, it's optimizing the single maximum reward achieved during an entire episode. That's it.
That sounds a lot simpler.
The core appeal is absolutely its simplicity and reward design. It's kind of revolutionary.
So if we only care about the highest reward the agent gets, how much easier does that make the job for the human engineer?
Dramatically easier. I mean, all you have to do is make sure that better states have bigger reward values. That's it. As long as the final goal state has the absolute highest reward in the whole environment, the optimal policy is the same, no matter what you do with the intermediate rewards.
Wow. So you're totally freed from worrying about complex time discounting or how intermediate steps add up.
Exactly. It's a huge weight off.
That sounds like a vacation compared to normal reward engineering.
But let's get under the hood a bit. Does optimizing for the max instead of the sum actually change how the agent learns?
It creates a massive advantage, especially in these sparse settings. And it all comes down to how information is propagated backward, a process we call bootstrapping.
Bootstrapping.
Yeah.
That's when an agent estimates the value of its current state by using the estimated value of the next state, right?
Precisely.
Yeah.
And in standard cumulative RL, the target value is always the immediate reward plus the discounted value of that next state.
Okay.
But since that next state's value is constantly being updated as the agent learns, the whole target is a continuous moving target until the system finally converges.
Which is why, in a sparse environment, it takes forever for that tiny signal from the distant goal to slowly creep all the way back to the start of the trajectory.
Exactly. But in max reward RL, this bootstrapping is just. It's far more efficient. The moment an agent finds a reward that's a new personal best for that trajectory.
A new high score. A new high score, yeah. The target value for that state propagates backward instantly, and it stays fixed. That information is locked in. It becomes a stable anchor for learning.
So once the agent finally stumbles upon that massive goal reward, the signal just jumps backward and influences actions way earlier without needing to slowly trickle down step by step.
Yeah.
That sounds incredibly efficient.
And they proved this. They used a simple 5-state chain environment. The goal was just to reach state S4 for a reward of 1, but they simulated sparsity.
Wow.
They made the transition into that goal state S4, very rare. They made it fail with up to a 90% probability. This is a lot like an agent searching a huge complex maze and only rarely finding the goal.
And what did that show?
It showed that for those high skip probabilities, the max reward approach converged to the optimal policy significantly faster. I mean, way, way faster than the standard cumulative approach.
So it confirms the whole idea. Max reward needs fewer of those rare goal-reaching moments to learn because the information is just so much more powerful when it arrives.
Exactly.
This sounds like a complete no-brainer for any kind of goal-reaching problem. I mean, simpler design, faster learning.
Yeah.
So why haven't we been using max reward RL for the last decade? Was there some theoretical elephant in the room?
What's fascinating here is that there were earlier attempts to formalize this, but they all fell apart theoretically when you tried to apply them to the real world.
Oh, really?
Yeah, these early models, some go back nearly 2 decades, were either just mathematically flawed or they were strictly limited to purely deterministic settings.
Meaning zero randomness, no random environments, no random actions from the agent.
Which, of course, is never the case in the real world, especially not with modern stochastic policies. And that was the critical roadblock. You can't just take the standard Böhmer equation, which is based on summing rewards, and swap in a max operator. It fundamentally breaks when there's any randomness involved.
Can you maybe walk us through a simple example of where that naive approach breaks down?
Absolutely. So imagine a really simple 3-state task. You have 2 policies, we'll call them Pi1 and Pi2. They both start at the same place, get a reward of 6, and move to a new state, S1.
Right.
From there, the paths diverge.
Okay, so far so good.
Policy Pi1 is risky. It has a high potential payout. From S1, it leads to a final state with a reward of either 0 or 12, each with a 50% chance.
High risk, high reward. Got it.
And Policy Pi2 is the safer bet. It leads to a final state with a reward of either 7 or 9, also 50-50.
Okay, so if we're trying to figure out which policy is better, the true expected max reward for Pi1 is actually 9, and for Pi2 it's 8.
Right. So Pi1, the risky one, is demonstrably the better policy. It gives you a higher expected maximum reward.
But if you use that naive deterministic math,
it gets it completely backward. The naive approach, it first calculates the expected reward of the next state and then takes the maximum. Right. So for our risky policy Pi1, the expected reward from S1 is just 6. So the naive value is max of 6 and 6, which is 6.
But for the safer policy Pi2, the expected reward from S1 is 8. So the naive value is the max of 6 and 8, which is 8.
Exactly. The deterministic approach incorrectly tells the agent that the safer policy is better. It leads the agent to choose a suboptimal policy because it doesn't correctly account for the potential maximum reward that's hidden inside those random outcomes.
That is a critical flaw. So the takeaway here is that just slapping a max operator on the old equation is useless in the real world. It seems like we needed a completely new theoretical tool to solve this.
And that brings us to the core theoretical breakthrough of this paper, which is the fix for that exact stochasticity problem.
So if the summation breaks down and the naive max operator breaks down, what was the insight that finally unlocked this for stochastic environments?
The key was realizing that to maximize the maximum reward, the agent fundamentally needs to track information about its past successes. It needs context about what it's already achieved.
So the agent needs a kind of built-in memory for its rewards.
Precisely. They introduced a crucial element, an auxiliary variable, which they call Y. For you, the listener, you can just think of Y as the agent's personal best scorekeeper for the current run. It's always tracking the highest rewards seen so far.
That makes a lot of sense. If the agent knows its best score is 50, it's not going to be satisfied with a state that gives a reward of 45.
Exactly. And to make this work mathematically, they had to redefine the entire problem. They call it an extended max reward MDP.
And what does that mean in practice? How does that look?
Well, the agent isn't just operating in the original state space, S, anymore. It's now an extended state space, which is the original state S combined with that memory variable Y. So the agent's view of the world is now this pair, S, Y.
Okay, so what's the massive implication of that? The optimal policy has to change, right?
The implication is profound. In standard RL, the best action only depends on where you are right now, state S. But in this new framework, the optimal policy must depend not only on the current state S, but also on the rewards you've gotten so far, which is tracked by Y. And if we connect this to the bigger picture, introducing MOA is what gives the agent the critical memory it needs. It's what allows it to make optimal decisions based on past successes, which is absolutely necessary in a random stochastic setting.
And what about the math behind it all? They mentioned something about A gamma contraction. Why is that such a big deal?
That's the proof that the whole system is stable. With this new extended state space, they could define a new Bellman-like operator. And by proving it's a gamma contraction, they assured that if you keep applying it, it will reliably converge to the true optimal policy.
So without that proof, the whole system would be unstable, and we couldn't really trust the results.
We couldn't. But because they solved the stochasticity problem and proved convergence, this theory is now robust enough to handle the randomness of the real world. And that foundation means that all modern RL algorithms, your PPOs, your TD3s, can now be adapted to work in this max-reward paradigm. It makes the whole idea finally viable for complex real-world problems.
Here's where it gets really interesting. Putting this new theory to the test in some seriously complex environments. They started with mazes, right? From the Gymnasium-Robotics suite.
They did. They ran tests comparing standard PPO and TD3 against their new max reward versions. And they tested across different kinds of rewards, from purely sparse to a dense distance-based reward, and also a special one called discrete shortest path, or DSP.
And that DSP reward was key for controlling the difficulty, wasn't it? They had a parameter, K, that could make the reward sparser and sparser.
That's right, and the findings were stark. The max reward approaches worked really well across the board for all values of K. But when A got large, meaning the reward was extremely sparse,
the standard methods struggled.
They struggled badly. The standard cumulative RL methods often just converged to suboptimal policies, constantly getting stuck in dead ends and failing to find the true goal.
So why is the max reward agent so much better at avoiding those traps, those local optima? Is it just the faster bootstrapping we talked about?
That's part of it, but it's really about the memory, that auxiliary variable way. Think about it. A standard agent finds a little corner that gives a small but stable reward. It might just stay there because the expected return for exploring elsewhere looks too uncertain.
Right.
But the max reward policy is conditioned on A. It remembers that it has already achieved a higher reward somewhere else. So it has no incentive to stay put unless it can beat its current high score. It's constantly driven to explore for a bigger prize.
That is a fascinating consequence of the extended state space. It literally forces the agent to keep improving.
And crucially, they also had to prove their fix for stochasticity worked in practice, not just in theory.
How did they test that one?
They made a stochastic version of the maze where random actions or slips would happen up to 30% of the time. The results were perfect validation. The new max reward TD3 solved it successfully.
The old naive version.
The older deterministic max reward TD3, the one that failed our simple three-state example, was, and I quote, highly inconsistent and unreliable. This really cemented the new framework's robustness.
Okay, but the ultimate test has to be complex robotics. They moved on to the fetch environments, right? Fetch slide and fetch push, using a sophisticated robot arm. Those are known to be really tough.
They are. In these high-dimensional problems, finding the goal is incredibly rare, and the standard cumulative TD3 algorithm, just like in other research, it fails to learn completely. There's not enough signal.
And the max reward version.
The max reward TD3 achieved a goal-reaching policy in both of them, both fetch slide and fetch push. It's a huge demonstration that this isn't just a novelty for simple mazes. It offers real performance gains in complex, realistic robotics where traditional methods completely fail.
So what does this all mean? We've seen that the max reward paradigm, which was once theoretically broken in stochastic settings, is now robust and gives these concrete performance boosts in really complex, sparse environments.
Yeah, we can really summarize the advantages for you, the listener, into 3 clear points. First, you get incredibly efficient bootstrapping. The moment that rare goal is found, its value just propagates backwards so much faster and more stably.
Second, you get this powerful local optima avoidance. Because the policy is conditioned on that memory variable y, the agent has this built-in history of its best rewards, which stops it from settling for good enough. It's always pushing for better.
And third, there's a subtle but important finding. Because that variable y brings history into the state, the value functions become inherently distributional. And previous research has suggested that this alone can have a really positive impact on learning, even outside of this max reward goal.
So max reward RL is proving to be a superior choice for goal-reaching tasks, especially the ones with sparse rewards or high complexity where, trying to engineer the perfect dense reward has always been the biggest headache.
Absolutely. The breakthrough here is how they integrated that history into the state definition with the Villi variable. It's just essential for getting the optimal policy. And this raises an important question for you to think about. In what other types of learning problems, not just goal reaching, but maybe tasks focused on safety or avoiding rare but critical failures, might optimizing for a non-cumulative objective combined with a historical memory component like Villi be a better path forward? It really makes you wonder what other core assumptions in RL might be missing that essential historical context.